Now, sometimes you're asked to complete wavefront diagrams, and whenever you're asked to complete wavefront diagrams, you have to draw wavefronts onto them. And so the first one that you might be asked to complete is reflection of waves. And reflection of waves would happen at a mirror or some kind of surface like that. If it was water, it could just be a flat surface and the waves would be reflected then. So reflection of waves with water is exactly the same as a reflection of waves with light. You will first of all have the same angle of incidence and reflection. So I'm just going to guess here, I should have had a protractor, but we'll say that that's the direction. And this angle should be more or less the same. We'll call it R. I think it looks a little bit smaller, but it should be more or less the same. If you're then asked to draw some more wavefronts onto your diagram, the wavefronts don't change at all, and the wavefronts are always drawn at right angles to the direction of travel, like that. So if we have a wee look at them there and see they're approximately, roughly about 1 centimetre apart there. And so if we are to draw our new wavefronts on here, they have to be at right angles to the new ray, and they're approximately 1 centimetre apart. So we'll just mark that on, get a couple on here. And so they're parallel to the one before it. So roughly there and roughly there. So they're more or less the same wavelength again. So lambda is the same. Now, the table beneath that just shows, very often you might be asked what has changed whenever your wave has been reflected. So your wave is still coming from the same source, whether it's light or from water, a source of water vibration or something like that, vibration in the water, but the source doesn't change, so the frequency of the waves doesn't change. So it stays the same. The wavelength does not change either. And since V is equal to lambda F, if those two don't change, V doesn't change either as the wave is reflected. So there's absolutely no change in any of the three, V, lambda or F, whenever you have waves being reflected from some kind of surface. The next diagram that you might be asked to complete is a refraction diagram. And a refraction diagram then is whenever waves are bent as they pass into a different medium. Now I've drawn this for light, and I suppose I should have gone back just to show you back here. I've sightened. Light is exactly the same as any other kind of wave. There are wavefronts in light as well, but the wavelength of light is so tiny. It's about 400 nanometers, so that's 400 by 10 to the minus 9. So it's not 0.0, or it's not point and I think 6 knots and then a 7 or a 4. It's really, really tiny. It's so small that we can't see any difference between one wavefront and the next. So wave looks absolutely continuous to us, whereas we can see in the ripples in the pond, we can see the difference between one wavefront and the next. So light does travel in wavefronts as well, we just can't see them. We just see it as a continuous ray. Back to a refraction diagram here. You have got some light or water passing into a different, well, light's passing from air into glass. This could be from deep into shallow water, if you're talking about water. Okay, so this will give you exactly the same idea. But we know that whenever light passes into a less dense medium, it bends towards the normal. Into a denser medium, it bends towards normal. So if I draw a normal on here, normal is always a line drawn at right angles, and I bend the rays towards it a bit. So we'll do this here. Then what you have to do is to join up your wavefronts in this new part of the medium that it's travelling into. So if I just join up, you can't create wavefronts nowhere, but you can on further on down, but along the surface you can't. But your wavefronts must be at right angles to your new ray there. So the ruler's going to help me here because there's a long line on it. So I'm just going to join that up there. There's my first one. And then these are parallel. And I'm going to join it up again. There's my second one. There's a third one. And a fourth one. Roughly. So you can see there that these rays are parallel to, or these wavefronts are parallel to each other, but they're much closer together than they were out here. And so you can continue these on in at approximately the same wavelength, and they have to be perpendicular to the ray travelling in. I'll just draw a couple of them here. So you can see what's happened here. The ray has bent towards the normal. The angle's smaller now compared to the angle going in. Whenever you join up the wavefronts in the glass, you can see that their wavelengths are much, much smaller, and you can continue that on in. So your wavefronts have to be at right angles to the ray. They have to be equal distance apart, but they must be closer together. They won't probably measure that on you, but they will look and see, did you understand that? So what has happened here then? Well, the wavelength has got smaller. Now, as it passes from air into glass, the source of the wave, which was a ray box, maybe if it was light, or some disturbance out in the water, it doesn't change just because the light passes into the glass or the water moves into a shallow area. There's nothing to change the actual source, so frequency stays the same. And if we write down V is equal to lambda f again, V is equal to lambda f. If lambda has got smaller and the frequency has stayed the same, and you're multiplying a smaller number by a similar number as before, you get a smaller answer. So that means the speed has decreased. And so the speed has decreased, the wavelength has decreased, and the frequency stays the same. If the waves were moving out of the glass, then you would have this similar thing again. You would have your waves bending away from the normal. Your wavefronts would be a further distance apart, and therefore the wavelength would be increasing, the speed would be increasing, but the frequency again would be staying the same. So this is the same effect if you have waves moving from deep into shallow water. It's got exactly the same effect there. The third one then is something called diffraction, and we're going to write down a definition of diffraction. So a definition of diffraction is the spreading out of waves as they pass through a gap. Now it could be round an obstacle as well, pass through a gap, but through a gap will get you your marks, through a gap. So if instead of having a gap you had an obstacle here, then the waves will also spread out as they pass around the obstacle. So we have two kind of effects here, a narrow gap and a wide gap. If your gap is fairly similar in size to the wavelength of your waves, you get a lot of diffraction. And your waves will be lovely and circular as they pass through there. Now you have to try and keep your wavelength about the same. And again, we'll just take a wee look at that with a ruler. That is approximately about 0.9. So your wavelengths are approximately 0.9 centimeters from each other. It's hard to make the circle pattern nice and even, but we'll do our best here. And then you could put another one here. So they have to look as if their wavelength is the same, but they've spread out. A narrow gap, you will have a little bit of spreading out at the edges just. And so if I just draw here, and a very, very slight curve at the edges, again it should be roughly the same wavelength, a wee bit of curving at the edges just. So the effect is most pronounced whenever you have a gap which is approximately the same wavelength, the same size as the wavelength of the wavefronts. So what has changed here? Well, nothing has changed. Okay, they've spread out, but everything has stayed the same. So the wavelength, the frequency and the speed stays the same. There's no change. So really the only one of those three things, reflection, refraction and diffraction, the only one that has changed is the refraction one, where the wavelength and speed decrease when it goes into a denser medium, or increase as they come out of a denser medium into a less dense medium, and everything else stays the same.